Welcome and thank you for completing the previous lesson. In this video, we'll bring together everything that we have learned about polynomial functions by creating a comprehensive summary of their key features and characteristics. So by the end of this lesson, you'll be able to identify and describe the end behaviors of polynomial functions, the number of turning points, identify the type of symmetry, the number of zeros, and multiplicity, increasing and decreasing intervals, local minimum and maximums, as well as absolute minimum and maximums. Now, this summary will prepare us for our next lesson where you will learn how to perform a complete analysis of the graph of a polynomial function. Think of this lesson as a comprehensive review to help you prepare. So let's begin by reviewing increasing and decreasing intervals. So what you see here is a graph of a polynomial function. And I want you to think, to determine the increasing and decreasing intervals, we must first focus on which key points on the graph. So always remember that increasing and decreasing intervals are separated from each other at the minimum or maximum points on the graph. So at the higher or lower points on the graph. So first, you will have to locate those points, and surprise, surprise, it's very nice that we can easily read these points in here. They're integers, integral values. So we will be labeling these points as well, because why not? And in the meantime, we will identify the x and the y coordinates. So this will be the point A, coordinates -3 for x, +2 for y. Then we have the point B down here, which has coordinates -1, and let's count here, 1, 2, 3, 4. We are down to -5. We have point C that has coordinates of +2 for x and 1, 2, 3, 4, 5 for y. So we have 2 and 5. Now, we can also start off here, since we're at it, identifying them or labeling them as minimums or maximum, absolute or local. So you know that the points that are turned down this way, so they are maximum. So I'm going to call points A and C maximum points. Now, point C is the highest point on the graph, so we'll call this the absolute maximum. And point A is a maximum, but it's max higher in this location, so that's a local maximum. We can only have one absolute maximum, obviously, so not more than one, because that's why we call it absolute. Now, point B is a lower point on the graph, and we're going to call this a minimum. And if you want to be more specific, we have to give it a name, whether it is local or absolute. As you can see here, the graph extends at both ends, which means the y values will be approaching -infinity. So the lowest values are going towards -infinity, which will make point B a local minimum. Now, let's begin by determining the increasing and decreasing intervals. So for this, if you remember, we start off by reading the graph left to right, just like we read a book. And this is where we start, and we see if the pen is going up or down. So it's going up all the way to the turning point A. And this will happen for the x values. Now remember, when the arrow goes down, the x values here are from -infinity all the way to -3 here. So that will make an increasing interval for the function. So we're going to say an increasing interval is from -5 to -3. So we'll continue walking on the graph. As you can see now, we have a graph that is decreasing, so the pen is going down, and this will continue, or will start at -3, and it will continue up to x value of -1. So we're going to say that the interval from -3 to -1 will be a decreasing interval. We'll continue with the next one. As you can see now, the pen is going up, which makes this an increasing interval, and the x values responsible for these increasing y values will be from -1 to +2. So we're going to join -1 to +2 interval to the previous increasing one. And we'll continue our journey here. Walk on the graph. You see you're going down. You make a turn. Remember, this is what we call an inflection point, but it looks like we're making a turn, but then we don't go all the way back. So we just continue decreasing here. So therefore, we're going to say that this entire interval here from x equals 2, remember that's where this decreasing interval starts, to x positive infinity will be a decreasing interval. So we're going to allow this interval from 2 to infinity to join the -3 to -1, and we'll unite these two intervals by this special symbol. If you remember, this is the addition, but this applies to adding sets of numbers. Now next we'll continue with the turning points, so the maximum and the minimum number of turning points. So if you remember about the max and min of turning points, that will depend on the degree. And we said that for odd degree polynomial functions, I'm quickly going to draw the graphs of a couple polynomial functions in here. So we have the graph of an odd degree polynomial function. Remember, we start with the line and then the cubic function and then the pentic function with a wider turn in here. So they can get away with no turning points. So it can have no turning points at all. Now, the even degree polynomial functions, on the other hand, will need to make a turn at least one. And the reason why we said is because even degree polynomial functions have their end behavior such that they decrease at both ends. So at the ends of the graph, the y values can be either both decreasing or they can be both increasing. Now, on the other hand, when it comes to odd degree polynomial functions, the functions can, or the polynomial functions of odd degree go towards opposite y values. So, and that's the reason why they can get away without making a turn, because they don't have to come back to negatives or they don't have to come back to positives, just like the even degree polynomials do. When it comes to maximum number of turning points, regardless of the degree of the polynomial function, it will work in the exact same way. We're going to say the maximum number of turning point will be one less than the degree. And as an example, I'm just going to bring here a third degree polynomial function. Remember that we have said that polynomial curves are lines that go up and down based on the degree of the polynomial function. So a third degree can have a maximum of 3 lines connected in a curve, and as you can see, it will make for a third degree 2 turning points, and for a fifth degree it will make a maximum of 3 turning points, and so on. We've analyzed this already. So it will always be 1 less than the degree, and 1 less than the degree, if the degree is n, it will be n minus 1 turning points. Now, the same thing applies to even degree polynomial functions. So if we have, say, for example, a fourth degree polynomial function, then we have the right to go a maximum of 4 lines connected to each other in a nice smooth curve to make the polynomial of 4th degree. And you see that 4th degree can have 3 turns, which is 1 less than the degree of the function. So maximum number of turning points doesn't depend on whether or not it is even or odd. We just know it's going to be n minus 1 turning points, whereas the minimum is specific to odd or even degree polynomial functions. So we're going to say at least 1 here. Now let's move on to the end behaviors. Now, end behaviors of functions, a very big component of graph analysis will depend on the degree, whether it's even or odd, and the leading coefficient. And we've said that all odd degree polynomial functions will behave like the line, which is the simplest odd degree polynomial function. So if a line has a positive leading coefficient or a positive slope as we are used to calling it, then we're going to say that as x approaches infinity, y will approach infinity. So the way we look at it is the right end where x increases to infinity is going up. That's why y approaches infinity. Whereas the left end, this is when x approaches negative infinity, has the y values going down to negative infinity. Now, if a happens to be a negative number, then we're going to say that all degree functions, doesn't matter if the degree is 3, 5, 7, the end behavior will be the same as that of the line with a negative slope, and that is when a is negative. So what that means is that as x approaches positive infinity, now this time the y values will go down. So that's the right end of the graph. So y will approach negative infinity. Whereas when x approaches negative infinity, the y values will go up. Now, when it comes to even degree polynomial functions, if you remember, that will resemble the end behavior of the graph of a parabola. So if a is positive, then we're going to say that x approaches positive or negative infinity will have the y values pointing up to infinity. So both ends will approach infinity. If the coefficient a is positive, but if a is negative, then we'll see that the graph will have an end behavior similar to a parabola that opens down. So in this case, we'll say that as x approaches both positive and negative infinity, we'll have the y values go down to negative infinity. And that's how we describe the end behaviors for any even degree or any odd degree polynomial function. So say you have a third degree, you go this way with a positive leading coefficient. You have a fifth degree, then with a positive leading coefficient, you're going to follow the end behavior of the line. So what happens in between, it's a different story. It depends on the degree of the function itself. Now, the number of minimums and maximums is related to turning points somehow, but there are some specific components of it that I want to mention and discuss with you in this video. So if we have an even degree polynomial function, as we mentioned before, then the graph of even degree with positive leading coefficient will need to have will open up. So, and I'm going to start off with a parabola here, which is the simplest even degree polynomial function. When a is down, it's going to open down. Now, when an even degree polynomial function has a leading coefficient that is positive, it will have an absolute minimum. And that is not something that I'd encourage you to memorize. It's something that I want you to visualize. So remember the connection that exists throughout or across all even degree polynomial functions and draw the conclusion right there. So if you have an even degree polynomial function with a negative leading coefficient, then the graph of the function will show an absolute maximum. Now, for odd degree polynomial functions, remember that they can escape and have no turning points at all, so they don't necessarily have to have an absolute min or absolute max. So if a is positive, they will behave, let's say I'm looking at the cubic function here just to make things more interesting, but the line can work as well. But lines don't make a turn at all. That's the reason why I don't want to choose the equation of or the graph of a line here. But when a is positive, it can get away with no turns at all. When a is negative, same idea, it can get away with no turns at all. Now when it comes to absolute min or max, due to the end behavior of all degree polynomial functions where the y values increase to infinity on one end and decrease to negative infinity in the other doesn't allow the graph to have an absolute min or absolute max. So we're going to say that odd degree functions do not have absolute min or absolute max. And what I'm going to do, actually, I just noticed this. So we're going to say that they do have an absolute min in here. So let's put a check mark in here. And the A negative will have an absolute max. So let's bring it here. I think I was being a little bit too specific when I was preparing the handout. So when an even degree polynomial function has a positive, it has an absolute min, it cannot have an absolute max. So you can put a cross in there if you want to complete this accordingly. And even degree with a negative can have an absolute max, no absolute min. Obviously, you can have one or the other. Now, odd degree polynomial functions can get away with no absolute min or absolute max, okay? But they can have actually a relative min and max. Now, all polynomial functions can have relative min and max points regardless of the degree, and that will equal the number of turning points. So we're going to say that this will be dependent on the degree and only on the degree of the function. So it doesn't really matter whether it is even or odd. So odd or even doesn't matter. So same idea for odd or even. Okay, or same rule. Okay, now when it comes to symmetry, we've mentioned two types of symmetry, even or odd symmetry. Remember, even symmetry is when the y-axis will serve as the line of symmetry, and odd symmetry is when the origin of the Cartesian plane serves as the point of symmetry. So we can rotate this graph around this point, and then this graph can become even this way, and that's what makes the symmetry odd. Now, remember that if the line of symmetry is not in the y-axis, let's say, for example, what I did in here is choosing the exact same graph. Let's see here, just so that. So I chose the exact same graph, but I just positioned it elsewhere so that the line of symmetry was not on the y-axis. So that doesn't guarantee even symmetry, because even though the graph in itself is symmetrical at both halves of it, so both halves of it can overlap, it is very important that the symmetry is on the y-axis. And same applies to odd symmetry. So it has to be, even though these two are same graphs, the symmetry has to be around the origin like this, and if you move it one unit up, down, so even slightly left, right, up or down, no longer has the odd symmetry. Now, how do we prove even symmetry? Remember that for even symmetry we check and see if the graph or the equation of f of negative x becomes the same as f of x. So we simplify that algebraically, and then if they're the same, then we're good to go. And for odd symmetry, so we are going to check and see if the f of negative x with a minus, so both the x and the y values need to be reflected. So we want f of x to be equal to negative f of negative x, and that's how we check that algebraically. And if you need more examples, you can go back to the lesson where we explain that in more detail. So, and you can explain this in your own words, how to determine even and odd symmetry algebraically. So step number 1 would be to find f of x, f of negative x, and then you have to check and see, is it equal to f of x? So if yes, then you're going to say, fine, it is. But if no, then you have to check negative f of negative x, and then compare with f of x. And if that is true, it has odd symmetry. And if it's not, then it doesn't have symmetry, and not all functions have to have perfect symmetry. So there is an infinite number of polynomial functions there, and very few of them would have symmetry, like comparably. Now, the number of x-intercepts, that's another interesting, very important, and very easy to understand and remember. Odd degree polynomial functions will always need to have at least one x-intercept. And the reason why is because odd degree polynomial functions at their ends will go in opposite directions, so positive and negative infinity. So what that means is that the graph will need to cross the x-axis. Another way to explain this is remembering that the range in odd degree polynomial functions is y any real number. And if y is any real number, it means that the y values will be positive, will be negative as well. And because they're continuous functions, when a function changes from negative to positive and vice versa, they have to go through their zero. So we need to have at least one x-intercept. When it comes to even degree polynomial functions, they can actually escape the x-axis without making any contact and no x-intercept. So we're going to say that the minimum can be even none. When it comes to maximum, oops, that is a typo, we'll have to fix that. But when it comes to maximum number of x-intercepts, that will perfectly match the degree of the function. So this is an example of a third degree, and here is an example of a sixth degree polynomial function with all possible number of x-intercepts. So we're going to say that that will equal the degree of the polynomial function itself, no matter whether it is even or odd. So about the multiplicity of roots, remember roots, x-intercepts, they mean the same thing. Sometimes we will see that the polynomial function could be in the form, say, x minus 1, x plus 2 to the power of 3, 4 minus x to the power of 2, and we can play with more degrees around this, and I am going to throw in a coefficient of 2. So we're going to say that when the power of a factor is 1, well, remember, first of all, I just want to mention something else before we move on. So whenever we find the x-intercepts, we have to make each factor equal to 0, and that's how we get the x-intercepts. So in this case, as you can see, we have an x-intercept at x equals 1, x equals negative 2, and x equals 4. Now remember that each factor will have different powers. So we have power 1, power 3, power 2. Now these exact powers indicate the multiplicity of the root. So x equals 1 is a root of order 1, we say. And let me just make it a little bit more obvious in here. So that's order 1, it matches the power. This one here, x equals negative 2, will be an order 3 root, or multiplicity 3 is the same thing. And lastly, we have a power 2 here, which will make this an order 2 root. So why are we interested in knowing the multiplicity? The reason why is because the graph of a function will have a specific shape depending on the multiplicity of the x-intercept. Now, when you look at the degree of this function, so the degree of the polynomial function here would be equal to the degree of all the to the sum of all the powers. So we look at the degree of every exponent of every factor that contains a variable. Don't forget, this is a factor as well, doesn't have a variable, it's a degree 0, so it doesn't contribute to the entire degree of the function. So this will be a degree 6 polynomial function. So we're going to say that in this case, the degree 6 will behave like a parabola that has a positive, let's say, negative leading coefficient in this case. So let's look at the leading coefficient since we're at it. So we have a coefficient of 2 multiplying coefficient of 1 multiplying 1 and multiplying coefficient of -1 here. We look at coefficient of x. So let's see what we get in here. So we have a coefficient of 2, which is multiplying 1 to the power of 1. Don't forget, those coefficients will be brought to this power as well. And then we have the coefficient of 2 to the power of 3. And lastly, we have a coefficient of -1 to the power of 2. Now, when you multiply all these numbers together, you get 2 times 1, 2. 2 to the power of 3 is 8. So 2 times 8, and then -1 squared is 1, so the coefficient will be 16. It's positive. So with an even degree and positive leading coefficient, we're going to say that the function will behave at the ends of it, will behave like the parabola that opens up with a positive leading coefficient. So the graph will start here and end in here, just like parabolas do. And now let's sketch the graph or the shape of this particular graph. So we have x-intercepts at -2, so let's say this is -2, one is at +1 and the other one at 4. So again, this is just a sketch, so it's not a very accurate graph. We're going to do this in the coming lesson, and we're going to say that the graph will cross the x-intercept at -2 with a multiplicity 3 root. So multiplicity 3 means that the shape of the graph at the root will be an S shape. So right here at this root, you're going to see this particular S shape, which we call a point of inflection. Now we're preparing to hit the graph again at x equals +1. +1 is a first order root. When the order is 1, it means that the graph will just intersect and get through the x-axis without making any, I would like to say, any stunts in there. Just get through it the smooth, simple way. And lastly, we're going to hit x equals 4. Now we're going to prepare at x equals 4 to show an order 2 x-intercept or multiplicity 2 by making a turn at 4. So when we have, it's an even multiplicity, that's why. So when you have an even multiplicity, the graph will make a turn at the intercept. And this will be the shape of the graph of this polynomial function. So you have a lot of practice questions that you may want to sit down and work on. I'm going to scroll down very slowly so that you have an opportunity to look at these questions and practice. Use your notebook to practice all these questions on your own. And I hope that you enjoyed this lesson. It's not a really new lesson, but it is good to take a break and make a summary of what you've learned and put everything together and see how they make sense. And, you know, in a way, kind of enjoy what you have learned so far and pat yourself on the back for it. So this would be the last page, so some communication and thinking questions in here, and you have the answer key provided as well that you can look at. And as always, thank you for learning with me, and bye for now. See you next time.